All right, slight technical issues now fixed. Okay, so I asked how everyone's doing today. I got very few responses in chat. It's Monday. I worked all weekend grading tests. You took the test on Saturday. So you're probably like, I'm a little. So let's try to get some energy up. Be more fun. I know I played music in chat before the class that was not exactly energy up music, but today's actually a really cool lecture, and it's a really cool topic. So let's talk about something kind of neat, and that's the area under the curve function. Please say hi to the TA that is in chat helping us today. Um, so, are there any questions about the quiz? Are we all good on that? I think we should be good on the quiz. Okay, so let's talk about this today. Now, um, let me talk just a moment about the test. I don't want to take up too much time. Right now, I haven't quite. So the first draft of the grading is done. In other words, the TAs have gone through and graded all the problems. But I have not finished going through all of the tests and just checking them, especially the proofs, because those I want to double check. Um, because some of you guys did things that are unexpected and not of the rubric, and the TAs might not know how to score them and everything. Not that that's any of their fault. It's just that some of them, if you don't have as much experience doing this, you don't always grab all the brilliant things that you do. And some of you actually did some pretty slick stuff, especially for the Rolls theorem proof. Some of you guys had ways of doing it that were not expected by the rubric that were actually really nice. So I've been just going through, and I already checked all that proof, but there's still the one with the trig that I wanted to look over before I released them. So you'll probably get grades back either tonight or tomorrow at some point. It'll probably be tomorrow before I have time to finish them all. Right now, the average is a 71-ish. The median is like a 72-ish. Again, I haven't gone over everything. Expect that to come up like a point or two, but not too much. It's about 4 points lower than normal for my class. Now, a lot of that's because the nature of the test changed. But two of the instructors. So there's two classes. Then me, there's like three. So there's classes that did very well. Not very well, like 5 points, 4 points higher than us. And then there's like 10 feet of crap, and then there's the rest of them. Um, and this class didn't drop off much from last year. Some of the classes did a big drop off from what they normally are, but two of the classes kind of maintained everything. I don't know what their secret is, but I'm going to figure that one out because they seem to be maintaining better. So if you have any suggestions, please, by all means, send me an email. Also, fill out the survey. I'm all ears. The other thing was that the testing method, there were distractions. One, I played music that was apparently bad music to play during the test, especially at the end. Made people panic. I actually saw some of that on your test. So I'm going to figure out a better way to handle that. Probably not playing music when time is up. Um, the other thing was that there was some non-smoothness with Proctorio and with a longer test. And I'm willing to, if you've got suggestions on how to make the testing process work better, so that you're not stressed about that process, rather you're focused on the test instead of all the other stuff, please send me an email. One suggestion was to have the test at a different time, not on Saturday morning. I can't do anything about that, but that is the final exam is like in the afternoon, but it's still going to be the same family thing, right? Because even everybody's family's home on Saturday, even people that are essential workers. So that was an issue. So hopefully you guys can figure out a place to take the final exam that isn't as distracting. But I know you're home, there's distractions, there's parents, especially with the long test, the finals 2 hours instead of the 90-minute thing. And it's hard to find consistent quiet time on Saturday uh, at 3 p.m. Uh, and I don't know exactly how we can make that happen. I'd like to, but I don't know how. So if you've got suggestions, by all means, post them on Discord, send me an email. I am all ears. It's enough about the test. I will be happy to talk to you about your test during office hours if you'd like, starting on Wednesday when I return them, if I manage to get them back like I planned to. Let's talk about the new material. So the way I do module 4 is backwards. Okay, and I usually get my module 4 is all about the fundamental theorem of calculus, and it's handled on the second to last day. And I think this is crazy because all of module 4 comes down to the fundamental theorem of calculus. So what I do is I start with that. Now, I don't prove it right away. We kind of play with it some today. But I start where most of the other sections end. And then I work my way backwards. Okay? And this has, usually my scores on the final are higher than everybody else's. And I think this is the reason. I mean, it might be something else that I'm doing. It might be that my students don't perform as well in test 3, and then they're like, oh no, I got to do the final. But this seems to be the approach that works. But it's completely different than the textbook in the sense that I'm going to use a different notation, and I'm going to start at the end and then kind of work backwards. Right, so everyone else today is doing antiderivatives. I'm doing the fundamental theorem of calculus, and then we're going to kind of move backwards from it. Okay, so I hope that I've established some trust on how you add this. 1 to 5, how do you feel about the plan? The plan is to start with the fundamental theorem of calculus and work backwards. How do we feel about that? 1 to 5. Okay. And as I said, I'm asking you for a leap of faith because this is different. And the research says that this is kind of a better way to do it. But of course, the textbook is 80 years old. Well, it's not quite that old, but it's old. And the guy has died, and apparently in his will, he said you can't change his textbook. So we're kind of stuck with what he did. But students have reported in the past if that this approach worked for them. So I'm going to go ahead and do it this way. And I think it does work better. Let's start with a motivating question. For the entire module, let me ask you this. What is the formula for the area of a circle? In terms of the radius. Someone post it in chat. What's the formula? That's right. Now, what is the formula for the circumference? Is that a pH or an F, by the way? Yeah. What's the relationship between those two formulas? Someone type it in chat when they see it. Yeah. The circumference why? That's kind of our motivating question. Why? Why is the area prime. Why is the derivative of area the circumference? Okay. What is the relationship between circumference and area, and why is that the same? And this question goes back 3,000. This is an Archimedes type question, 2,500 years. Okay. Archimedes was the person who first wondered this. He didn't have formulas for the derivative, but he was the first person to ask about the relationship between circumferences and areas. So this problem is old. It's actually older than differentiable calculus. The question of the area of a circle is one of the oldest questions in mathematics. And the question is, how do you find it, and why is this the case? Okay. So that's kind of our motivating question. And this only works, by the way, for a circle. It'll work for ellipses, but you have to modify the formulas a bit because they're not quite as clean. So in order to answer this question, so how do we feel about that 1 to 5, this relationship, and why it should motivate us to wonder about mathematics? How do we feel about that as kind of a motivating thing? Are we intrigued? How do we feel about this? All right, well, let's talk about why. In particular, we want to talk about a function. So remember from last time, remember the definition of the max function, okay? So this was that let f be continuous. Okay. All right. So let f be continuous on an interval d, and let a and d be something called the base point. And we wind up with this function here. We wind up saying that max fa of x equaled, and then there was this complicated thing, max, the maximum of the set f of t, so that t was in the closed interval ax, and I don't want you to get like too hung up on the definition, but we had this thing where the base point had some properties, and I wound up with this continuous function. How do we feel about that one, 1 to 5, this function? And kind of the idea that it had parameters, and it was something that told us about the graph of f. All right, so this was a parameter. So I had this kind of fixed A and kind of this fixed F, and I wanted to talk about something about the graph. Okay. hold on to your confusion about that problem, because this one is a little bit more confusing than the one we're doing today. But the one we're doing today will give you information about this one, right? The intuition for some of it, the one we're doing today, the area under the curve, is a little easier. So let's define a new function. And again, this is a function about f. So here are the important things. Let d be an interval. Closed, open, I don't care. Let a be some fixed point in D. This should be an N. Let fixed point in D. I'm going to call that the base point. And let f be continuous. And I'll get rid of this. That should be an Oxford comma there. Right there's an Oxford comma. And let f continuous on D. Okay. The area under the curve function and the notation for this is different in my class than you're going to see elsewhere, okay? So there are two notations for the AUC function, okay? One of them is a more common mathematical notation, and it's not this one. This one, however, is better for our purposes today and for the foreseeable future, okay? So, not the foreseeable future. At some point, we're going to switch notations to the more common one. But this particular notation, there are two reasons I do it. One, because it's better for what we want to talk about. And the second is that if you go to medical school, this is the notation they use. Everywhere else, they've gone to the other notation, which we'll cover. Okay? That's fine. But for today especially, but, for a while too, we're going to use this other notation, the medical school notation. All right? That's where you see this. And for one purpose, and one purpose alone, it's so much better than the other notation that we're going to use it in this class. Measures the signed area between the graph okay? So how do we feel about this definition? 1 to 5. All right. Before doing any examples, how do we feel about this? What is signed area? Let's talk about that. That's a good question. That's a good question. What is signed area? I'll get to that in a minute. Let's see. Now, my computer's calculating the example. So let's take the function 1 plus cosine of t, and let's let our base point be 0. Now, give me a moment here. My computer, it's kind of getting really warm, so, the processor is trying to conserve itself. It's, this is a 3-computer, 3-tablet lecture here, because the software is only on my laptop and it's not on my, well, it is on my computer, but in order to access it from my computer, I have to have to log on to the VPN because the license requires it. Okay. So here's the function. So what I'm going to do is I'm going to start here. Let's do, this is better. Here it is. So what I'm going to do is I'm going to start here. My base point is 0. And I'm going to ask myself what AUC F0 here looks like. So when I hit play here, let's see what happens. So as I hit play, as X moves, does everyone see this? As X is moving, I'm sweeping out area under the curve. Okay? The area I'm sweeping out is the area between the axis, right? And the graph of F and the axis. All right. So I'm starting from 0 and I'm moving to the right. I'm moving from left to right. And as I move from left to right, I'm sweeping out area under the curve. And this function measures the area beneath the curve. It measures the area between the curve and the x-axis. So it accumulates the area. How do we feel about that, 1 to 5? Okay. Do I have a how do we feel about that, 1 to 5? This idea here of the area being swept out as I move to the right. So I'm starting on the left, I'm starting at my base point, and then I'm just moving to the right. Okay. Let's do another example here. Here we go. Now I'm going to start with, let's see, where does this one start? Now I'm going to start at 1. Instead of starting at 0, I'm going to start at 1. So this is AUC with a base point of 1. And ignore the numbers here because the program for this is an old version of the program. The current version of the program is on my computer at my office and not on my laptop. So I don't have access to the current version right now. So I had to use the one from 2 semesters ago. So the notation's a little different. But as I start from 1, as I move to the right, I'm sweeping out area. How do we feel about that? 1 to 5. This idea of moving to the right and sweeping out area. Oops. My TA is having issues with Twitch. That's why she's not. Yeah. Okay, let's try this again. Okay. So, same question. How do we feel about this idea? I'm sweeping over to the right. All right. So, going back here, notice here that when F here, if I come back here, notice here, F of 0.5 on this question is 1.6. So now I'm going to add the area as I move along to the right. Do we see that? And here, where f of x equals 0, I'm not adding any area. And then, as f increases, I'm adding more and more and more area as I move to the right. But notice here, my area is not decreasing. Okay? I'm starting from where I am, and I'm just moving to the right. Okay. All right. Well, someone asked me a question. What was this signed area business? If my x is below the x-axis, if my f is below the x-axis, oops, wrong one. If my x is below the x-axis, I'm going to add negative area. Okay? In other words, I'm going to have area that's in red, that's negative area, and I'm going to have area in green, that's positive area. So as I move to the right, if f is above the axis, I accumulate positive area. Whereas if f is below the axis, I accumulate negative area. So how do we feel about this idea of negative area, 1 to 5? I define it as positive area if I'm above the axis and negative area if I'm below. Okay. So I've got positive area above and negative area below. So here's my question. If x is above the x-axis, okay, and as I move to the right, am I increasing? Is my area under the curve increasing or decreasing? As I move to the right, if x is above the x-axis, if f is above the x-axis, is my function increasing or decreasing? Is area increasing or decreasing? Right. Now, if I'm below the x-axis and I move to the right, is my area increasing or decreasing? My total area. Exactly. So there's an interesting property of the AUC function. Okay. Well, let's do that. Interesting properties of the AUC function. Okay. If f is positive, then AUC FA of x is increasing as I move to the right. If f of x is less than 0, then AUC FA of x is decreasing as I move to the right. That's interesting, isn't it? Huh. Let me ask you another question. Where is this function maximized? Where have I gotten to my maximum point on this function? It's not here, right? Yeah, it's here. In other words, it's when I cross the x-axis, going from positive to negative. Interesting, right? Because if I hit play now, my function's decreasing. I'm adding negative area, so not the function's decreasing. My AUC is decreasing, right? I'm adding negative area. Forget that little artifact. That's an artifact of the programming. That shouldn't be there. That should be green. I can make that go away, but it'd like kill my computer because it'd take too many resources to do it at that level of detail. Yeah, so as I add here, I'm going negative area. Yeah. In other words, that's interesting. Let's write that down. AUC FA has a max when F goes from above to below the x-axis. That's interesting. How do we feel about that? 1 to 5. Huh. One to 5. How do we feel about that? Oh, now we got 2 poles going at the same time. Kind of interesting property. Okay. Well, let's do one for a simpler function. Okay. Let's look at AUC. Let's let f of x equal 1/2 x. Let's do another example. Okay, let f of x equal 1/2 x. Let's do a different one. Let's do f of x equals 2x. Now let's do 1/2. I did 1/2 x. I did x 2x on the last one, so let's do 1/2 x. Let a equal 0. Okay. This function let's see, what's this function look like here? Oops. Function's going to look like this. All right. Right there. So if x is 1, what is this function? So if x is 1, y is 1/2. If x is 2, y is 1, and so on and so on and so forth. So the graph of this function looks like this. And it goes -2. Now, what is the AUC? How would I compute AUC F0 of 2? In other words, how do I compute this area right here? Well, what would be the formula to compute that area? What is this? What is this figure? What does the area look like? Yeah, it's got a local, it's the area of a triangle, isn't it? So what's the formula for the area of a triangle? Right? This triangle has a base of 2 and a width. I'm using that because I don't want to use the word height, because later on, this base of 2 is going to get the variable h because it's French. And that width, or the height, is 1. Right? So the area of that thing equals 1. What about AUC F0 of 4? Well, now I'm talking about this length here. I'm talking about this area now here. Now I'm talking about that shaded green area. So I'm talking about 1/2 times 4 times, what's the height here? The height here is 2. How do we feel about that 1 to 5? So all I did was I took the area of this triangle, right? I wanted to measure the area under this curve. So I took the height and the width here, right? I went from 1 to 4, and then I went, so this here and this here. Okay. What about for a generic x? How would I compute that area? How would I compute the area for a generic x? Well, let's see. I've got 1/2 times whatever the x value is, times whatever the y value is. Okay, and the formula to find y is 1/2 times x. So I've got 1/2 x times 1/2 x, which equals, this right here is f of x. And that equals 1/4 x squared. How do we feel about that one, 1 to 5? This idea of finding a generic formula by just plugging in the x. Okay. All I did was take the width of this thing and multiply by the height. So I took the width and I multiplied by the height. And I wound up with a formula, right? So if my formula was 1/4 x squared, so if I use my formula, I get AUC F0 of 8 equals 1/4 times 8 squared, which equals 1/4 times 64, which equals 32, half of that. What have I got? 16, right? Yes. Yes. Okay. So I have a formula here for the generic thing. What happens if I take the derivative of that formula? What do I wind up with? That's kind of interesting. 1 to 5, how do we feel about that? The generic formula, and then I take the derivative of it. And I wound up with f. It's kind of interesting. Let's change the base point. We have something that's interesting here. Let's change the base point. So f of x still equals 1/2 x squared. But now let's let a equal 2. So let's copy all of this stuff here. I didn't get my axes, did I? But now what I'm going to do is I'm going to change the base point. And I'm going to change the base point to 2. So here the base point was 0. Here the base point was 0. Oops, sorry. Yes, you're right. Okay. Here the base point is 0. Up here the base point was 0. Now the base point is 2. Okay. Now, here's my question. How do I get AUC F2 of 6? In other words, what I want is this area here. And it should actually be in green. Okay, so how do I get that area? 1 to 5, how do we feel about the question that I'm asking? I want the area swept under the curve from 2 to 6. Okay. So 1 to 5, how do we just feel about the question? Okay. All right. So let's look at it. How could I get at this? Any ideas? Yeah. What if I take the entire triangle and then subtract the little one? What does that look like? What if I do this? What if I take the big one and then subtract the little one? Let's see. So that would be 1/2 times 6 times 3 minus 1/2 times 2 times 1. So this is going to wind up being 18 over 2, which is 9, minus 1. That's going to be 8. I could also do that. I could do the area of the rectangle plus the area of the triangle. But I want to get at something here. I want to get out that this right here was AUC F0 of 6. And this right here is AUC 0 of 1. I'm sorry, of 2. All right. I'm trying to get at this fact here. So I have another property of the thing, right? Let's do a more generic one. I now have the AUC F2 of X generically equals 1/2 X times F of X minus 1/2 2 times 1. This bit right here means that this right here is AUC F0 of X minus AUC F2 of X. I'm sorry, F0 of 2. And this is just a number. How do we feel about that, 1 to 5? Okay. I'm just exploiting areas. It's interesting. Notice also one other little interesting thing about this. D over dx of AUC F2 of X equals D over dx of 1/4 X squared minus 1, which equals 1/2 times X plus 0. Okay. So now I have an AUC. So how do we feel about that idea, 1 to 5? This idea that I could change my base point, and this is the formula for doing it. Okay. Okay. Are there any questions about this? I don't see many people asking questions. All right. Okay. Now, somebody give me a function whose derivative is 1/2 is 1/4 x squared. Okay, so is that whose derivative is 1/2? I'm sorry, 1/4 x squared. I'm sorry, not whose derivative is 1/4 x squared, whose derivative is 1/2 x. So give me a function whose derivative is 1/2 x. Any function whose derivative is 1/2 x. Okay, so 1/4 x squared plus 5. Claim. Okay, the first is that this is nothing but a vertical shift of the AUC function. In fact, it is an AUC function for some base point. Okay. Now, why do I know that this is nothing but a vertical shift of the AUC function? Why do I know that any function whose derivative is 1/2 x is going to be a vertical shift of some AUC function? I know that because of that. Remember that last thing we proved in the section for the mean value theorem? That's how I know this. Right? Because the two functions have the same derivative, they're nothing but vertical shifts of each other. That was that last thing we proved in the mean value theorem section. Moreover, right, I can use G for any valid A. So I claim that AUC, what was the one we did before? The one we did before was with a base point of 2. So I claim AUC F2 of x equals G of x minus G of 2. And look at that. How do we feel about that, 1 to 5? Okay. Let's do this in blue. All right. Are there any questions right now? And that's it. Okay? That's what we've been playing with this whole time. This is called the fundamental theorem of calculus. Now, of course, the first question, is this going to be on the test? Uh, hmm. Let's see. The class is called calculus. And this theorem is called the fundamental theorem of calculus. So let's see. The class is called calculus, and this is called the fundamental theorem of calculus. So do we think this is going to be on the test? Nah, no, right? Can't be. Yeah. As a matter of fact, this is the test in a very real way, okay? Everything that's new from Module 4 can be boiled down to this right here, Okay, everything, which is why I do it first. Okay, we're going to prove this, not now. We need a lot more pieces to prove it. But this is the whole thing. Okay, how do we feel about this theorem, 1 to 5, the statement of the theorem? FTC stands for Fundamental Theorem of Calculus. It has two parts. The hypotheses are both the same, right? F is continuous on D, and that continuity is extremely important. Okay? So, let me do one quick example of exploiting this. Okay? I've got 5 minutes left. So, example. Compute d over dx of AUC. Let's do this. Let f of x equal x cubed. Compute AUC, compute the derivative of that. Okay. Well, I put FTC1 over there. I have to name this theorem. Every time I use this theorem, I'm going to name it. FTC1, I'm going to get x cubed. Period. End of discussion. Compute AUC F 4 of x. AUC F 4 of x equals. Well, note that g prime of, so if g of x equals x to the 4th times 1/4, then g prime of x equals x cubed. So by FTC2, I'm going to wind up with g of x minus g of 4 equals 1/4 x to the 4th minus 1/4 4 to the 4th, which equals 1/4 x to the 4th minus 4 cubed, which equals 4 times 4 is 16, times 2 is 32, times 2 is 64. How do we feel about that, 1 to 5? Okay. All right. Let's do one last example. Compute d over dx AUC F4 of 5x. Okay. Well, I'm going to call this U. And I'm going to do this. D over dx of AUC F4 of U equals FTC2, comma, chain rule. So I'm going to apply two theorems here. The first one, FTC2, FTC1, and the second one, the chain rule. I'm going to get F of U times D over dx of U, which equals F is still x cubed. And then I created U, so I need to sub in back. Equals 5x cubed times 5. All right. So I'm out of time. Let's just go over what we did. What we did was we went over the area under the curve question. We asked this question about the relationship between the circle, the area of the circle, and the length of its boundary. We went over the definition of the area under the curve function, and we talked about the fundamental theorem of calculus. Next time, we're going to talk about what happens if x is less than a, and we're going to talk about more properties of this function and how to compute these antiderivatives that you need in order to use the FTC. There will be WebAssign up. It's not up yet, but there will be WebAssign for tomorrow. This right here, and there will be a quiz for Wednesday. This right here, the statement of the fundamental theorem of calculus, will occur on every single quiz from Wednesday to the final exam. Every single one. Okay? The sooner you learn it, the happier you're going to be. There's several ways of doing it. I did a slightly different version for the 9 a.m. class. The 9:30 class than I did for you. Both are perfectly valid. And there is another version that's in your textbook. I hate that version. You can use it, but it's actually more confusing. So memorize the fundamental theorem of calculus. We're going to be using it again and again and again. In fact, just about everything we're going to do, this entire class, for the rest of the time, comes down to the fundamental theorem of calculus. All right, are there any questions? Okay. In that case, I am going to jump off Twitch, and I'm going to jump back into audio chat on Discord where you can ask questions. Then I'm going to take a quick break, and then I will be doing office hours. Thank you.